Good morning or good afternoon, depending on where you're coming from. I want to welcome you to today's presentation on the EPA's refrigerant ruling, specifically how it impacts walk-in chamber design. My name is David Craig. I'm out of Rochester, New York, and I've spent the last 30 years or so traveling all over the US and Canada and even parts of Germany, working with end users involved in a variety of applications, cell and gene therapy, viral vector technologies, API storage, and even getting into some complex clean room design issues. It's been an awful lot of fun because I go to a lot of different places. I talk to a lot of different people, and they ask me a lot of questions, which is why I'm very happy to have the most appropriate named person to be working in refrigeration with me today, Nate Fries, because I'm going to be bouncing a lot of these questions towards him. Go ahead, Nate.
Thanks, David. My name is Nate Fries. I'm a project developer here at FARRAR. My role is to kind of work as the bridge between the customer, the engineering firms, architects, and our internal staff to put together the right solution for the clients. I've got 20 plus years in the business, kind of up and down the mechanical refrigeration business, all aspects. So I have a fundamental understanding of the site, conceptual, all those factors that I use to make decisions. Go ahead, David.
So what are we going to talk about today? Well, obviously, we want to review the EPA's Technology Transitions Program. That seems to be first and foremost on everyone's mind, and rightfully so. We're going to answer the timeless question of one-size-fits-all refrigerants. Do they exist or do they not? We're also going to take a look at things based on an application as opposed to specifically a temperature range. There's a few things that can be done in terms of the type of refrigerant and overall design. And then we want to really get into balancing the sustainability with energy efficiency. A lot of times we're shooting so hard for that low GWP refrigerant and reducing that carbon footprint that we don't look all the way down the line and realize that we might be using more energy than we are in the current system and putting more carbon into the environment than we would with the new system. So we always want to be very careful and take a look at that. So right off the bat, we have a poll for you. And this is one that we encounter quite a bit, and that's, are your projects being delayed due to uncertainty around the EPA allowable refrigerants? I'll give you a minute or so to complete that. One of the things we run into, obviously, projects get delayed because of a number of different reasons. They might be economic. This could be a brand new building where the construction delays, or if we went back a couple years when the supply chain was really disrupted, you could have lead times on some HVAC equipment of up to a year or two. So that can cause an awful lot of issues. So very curious to see what the responses here will be. So if you want, we can take a look at the results from that poll if people have had enough time.
So it looks like these results, 80% of the audience said no.
Okay. Perfect. That is interesting. Kind of falls in line with what I've been seeing. So what to know about the technology program, the phase out situation? Really what it's a couple things to be concerned with. There are really two pieces of data. Number one, it's effective on January 1st, 2027. So we still have some time, a little over 2 years left. The refrigerant mandate is that all new refrigerants must have a GWP, global warming potential, of 700 or less. So what it's really designed to do is set the limits on the use of some really climate damaging HFCs, gets down to specifics in terms of when it's associated with a refrigeration system or a cooling system. And again, it bans the installation of refrigerants with a GWP above 700. Now, there's an exception to that. If your applications are below minus 50 C, those are exempt, primarily because there just isn't a refrigerant that's available now that can handle that temperature range and still be under that GWP goal. The SNAP Rule 26 is already in effect. So there's a lot of different information that's coming around. You know, the question I've got for you, Nate, is a lot of these refrigerants are going to be phased out over the next 2, 6, 8, and 10 years. What's going to happen to, you've got a system right now where the refrigerant is going to be phased out. What's going to happen over that period of time? Will customers still be able to obtain the refrigerant for a recharge? Is there going to be a price impact? Anything like that?
There is, of course. So as we're driving down towards lower impact on the environment and phasing these out, they are all different. Each refrigerant is on a different schedule, but you know, on average, around 10 years. There's steps within that phase out, which they will reduce their production of new refrigerant. And then basically we'll be using recycled and a lower quantity of new refrigerant. So that will, over time, as the production gets lower, increase the cost for servicing existing systems. Now, it won't be just gone in 10 years. The complete ban or phase out takes another few years to manage that. But for new systems, that is much quicker.
You know, coming back to the no one size fits all refrigerant, there are a couple out there that that are extremely popular and people have an awful lot of questions regarding, is in search of that. So we've got the R290 propane, carbon dioxide, and ammonia. So if I start to take a look at ammonia, typically what I'm seeing with that is that's being used in a lot of warehouse applications, very large distribution centers, and very large rooms. It's extremely popular from a GWP standpoint because it's at a zero. It's got great thermodynamic properties and it's cost effective, but it's not compatible with copper. And copper is an ingredient that's used in almost all the other different components just because of its heat transfer capabilities. So I've got to imagine that the differences in design that are going to cause some issues. Maybe it's a cost or effectiveness issue. Have you run into any of that, Nate?
Yeah. So, you know, traditionally ammonia is more what we call large industrial or large scale warehousing refrigerant. And that's because of the toxicity issues and code compliance problems that are associated with putting it in an occupied building. Even in the industrial setting, we have to have alarming, you know, in the mechanical rooms, we have to have positive air exchange if there is a leak. So there are many concerns. It is also slightly flammable. So that's another con I would put on that list. And there's legislation they're looking at. There's ways we can do some things. We're moving towards that. Again, we don't want to sit still, right? Technologically, we want to be constantly looking forward. So smaller package units, using it as the primary refrigerant outdoor location, charge limiting, things like that are all kind of on the table to help utilize it in other applications.
So can the design features help mitigate some of the safety concerns then?
Some of it, like the charge limiting and stuff, that's going to be a big one. And then again, you know, alarming, isolation valves, all things like that. Again, it's really, every time we look at this, we always want to make sure we're looking at what's the most feasible that's going to get the job done effectively, efficiently, still try to meet that carbon goal, you know, and keep it simple, we'll call it.
How about from a cost standpoint? Is an ammonia system the most expensive, or is it?
So it's usually just in its current format, as you know, most of it's distributed systems. So you're talking about a large plant with a large weight of refrigerant with transmission piping. Usually we're always using carbon steel, large diameter piping, distributed loop piping, and sometimes move to stainless for longevity if the customer is willing to go to that extra. So it is a little more intensive on the install. And the weight in one system, where in this field where everything is redundant, right? It's 2 is 1, 1 is none. But the system like that isn't as effective because if you have a mainline leak, you've got to shut the system down and then we lose the box potentially. Whereas in a, you know, a food warehouse or something, there's not as much risk to the product.
Understood. This is one of my favorite ones is propane R290. It's extremely efficient. It's non-toxic, but it has one little problem with it, is that it's flammable. It has very, very low charge limit, so we can't use an awful lot of the refrigerant on its own. And that kind of hurts if you want to have a very large size, let's say a -60 or a -80 room. I always find it a little ironic that the charge limits are controlled so tightly in this type of an application, but I can put 40 pounds of it 15 inches away from an open flame in my barbecue grill in the backyard. But I guess there's not much that can be done about that. One of the questions
Yes.
that came up with me is if there was a leak, usually you could smell it, but I understand that is it the scrubbing process takes that odorant that's added out of the propane, which adds to the danger factor?
Yeah, so we use filter dryers in all the systems, and they do diminish that, so it's less pronounced or noticeable. They are working on other agents to try to improve that. But yes, the charge limits right now are 150 grams a circuit, 300 grams total. They're trying to pass 500 right now. So we use them mostly in very small chambers where we have local rejection of heat because we can't have transmission piping just to the charge limits. But it is quite efficient. And, from that perspective, it's good for very small installations, under 200 square feet roughly.
Are there any design changes coming that would maybe make that a little more widely acceptable, or are we kind of stuck in the current situation with how much and of the propane that we can use?
Yeah, with current legislation and the way everything is, that's where it'll be for now. Again, legislation is constantly evolving, code requirements throughout municipalities are changing all the time. So we're waiting for the UL and all that to make more decisions to try to utilize it more, as well as, equipment wise, putting more safeties in place.
Carbon dioxide, which is one that I find even more ironic than the propane in my gas barbecue grill, is the fact that we're using a carbon-based gas to reduce our carbon footprint because it's such a low GWP, so it's non-explosive. I get a lot of questions about CO2, and much like ammonia, they seem to be driven by very, very large projects, warehouses, distribution centers, logistics agencies, and things like that. Is there anything coming down in the future or any design changes that can be made to use CO2 in a smaller application? Let's just say it's a 10 by 30 minus 20 room. Is there anything that can be done to make that more cost effective?
So as technology evolves, of course, right, and adoption takes hold, you do get reduction in cost. Now, to your carbon comment, well, it's kind of like recycling, right? It's already in the air, so we're just taking it, condensing it, and reusing it. So, and in the spirit of that, it's not that bad. In terms of CO2's overall benefits, again, recycling that carbon. The downside is, to circle back on Craig's comment at the very beginning, which is talking about that balance, marrying or weighing the savings on CO2 and on GWP versus the potential energy cost. So CO2 is inherently a little less efficient. We can do some trickery to improve that, right? Optimize some things to make it a little bit better. And it has a limited range. So it covers the widest application, we'll call it, of the refrigeration need, but it is limited to -40. And that's because at that pressure and temperature, you're approaching triple point. So any drastic changes quickly due to a service event or a mechanical failure, and you have dry ice in the pipes, and then you've got a service problem. So there are limitations in terms of that. In terms of equipment, there's a couple ways to do it. All the rage right now is transcritical systems, trying to only use the CO2 as the primary refrigerant for the entire system, the least efficient way to do it. There are some things being done. You can go to adiabatic condensers and such to help optimize it for most of the run cycle of the year. And then the next step from that would be doing a cascade system where you use a secondary refrigerant to do the final rejection of heat, and use CO2 as the primary, where we can keep it in the low enough pressures to keep it subcritical and keep it in an efficient zone.
So I'm gonna have to imagine, does that add to the price, the overall installation?
It is.
Cost?
Because of the pressure that it's at transcritical, you have to use a particular type of embedded copper piping, or you can go with full stainless installations. There's special equipment that's needed to service it. Your traditional service tools don't work because of the pressures again, and we have to keep them clean. We can't contaminate the system. So there are always caveats that you have to consider that. Technicians are being trained on it, but it's not what I would consider mainstream yet. So there is that challenge. There's a little bit of cost, a little bit of service trouble with getting the right people on site to do the work day two. And that's kind of like I said, newer technology, that's always a challenge.
Okay. Hopefully that as this technology isn't so new, we can do some things that, the costs kind of come down and make it more applicable to other applications.
Yeah, and I kind of skipped over your first question there real quick, David, just to circle back, was, there are some small systems now. We have a standard condensing unit that we can do, in a fairly wide range at -20 that's transcritical. And as we keep going, we're going to continue to downsize everything to utilize that, because really it is, when you're looking at it from a long-term perspective for the client, if they don't want to deal with the next refrigerant or the next refrigerant, it's probably the most fits the most range that we need, that would provide the most to the client right now that we could do today.
So hopefully this could someday become the magic bullet, the one that'll handle a pretty broad temperature range.
Yeah,
and be able to do some smaller size.
Yeah, there's never one size fits all perfectly, but yeah, for a large swath, we could cover some ground.
Well, it's time for another poll. And this is one I'm very interested in as well, the results. What's your highest priority when it comes to temperature controlled environments? Are we looking at the upfront cost, annualized costs? Nate just mentioned with CO2, the higher pressures, you need some different equipment, and technicians have to be trained. Energy efficiency, or is it carbon reduction, that net zero goal? Is that what's the number one priority? Kind of stepping aside the costs, just what would your clients like to achieve with that? So I'll give you another minute or so to complete that poll. Nate, while they're taking that poll, so some of the things that you mentioned before, is that why we're running into CO2 and even ammonia just on the large scale facilities?
Yeah, because your charge limitations on some of the other alternatives, and again, catching up regulations, right? That's a big thing we'll talk about, is regulations always are lagging as they introduce new refrigerants, new, things they want to do in the market. That all has to go through the UL, ASHRAE, and then you turn around and have to go to the local municipalities, depending on the installation, and wait for them to adopt the same thing to approve it in their area.
Let's see. What do we have from our host? What do we have in terms of the poll results?
So it looks like annualized cost is the number one highest priority, followed very closely by upfront cost.
Okay, interesting.
So it's cost is always an issue, but it's kind of surprising at the lesser on the carbon reduction. There's a lot of large corporations that are pushing us pretty hard for carbon reduction.
Definitely. Oh, we learned something today. All right, so we've talked about ammonia, CO2, the R290. They've got their uses, they got their benefits and things, but what about some of these other refrigerants? They still fall well below the upper GWP limit. What do you see as their good and bad sides, Nate?
Well, what I was just mentioning was waiting for things to catch up. So 454 series has been in testing for a long time. It's been in kind of approval phase for quite a long time. And that's because those are A2L refrigerants. So those are what we classify as mildly flammable refrigerants. So they're not an A3 like propane, which is the big boom. These in just the right conditions will, ignite. So there are charge limitations that are put on them. The latest SNAP 26, has opened the door a little bit. So like 454A, they've limited to 200 pounds. 454C, technically, in its current way it's written, there is no limit. But again, this is where we have safety. There's going to be other safety controls on the system to make sure that, because it is possibly flammable, that we're making sure if we do have leaks and issues like that, that we're controlling the refrigerant where it's at and what it's doing. Again, no magic bullet. 454C is going to be probably the most popular for kind of full range, where like 1, 2, 3, 4 is more for what we'll call medium temp and or secondary systems, chillers, etc. In terms of the GWP requirements, most popular because of California CARB is going down to 170. So that will also push 454C to be kind of the go-to for everything in that market. Washington has also now adopted essentially the same thing as the CARB protocol. So they'll be in the same boat. There are, again, pros and cons, right? So as we've driven to this lower GWP, we had to use a propane base, which has made it mildly flammable. If we go back to the old refrigerants of the day where we loved them and they were bad for the environment, but they worked great, over time, efficiencies went down a little bit. So 454 is very comparable to, let's say, 448, 449 in terms of its performance. So really not all that bad. As you get in the lower temperatures, we get pretty low pressure. So it's going to be capped again at about -40. And then we have to look at, cascaded systems and 508.
Are there any other states besides California and Washington that have taken the EPA number and drastically reduced to their own? Or is that just at this point limited to those two states?
That's the two that are on the books, but we can expect kind of the major metros will probably follow suit. Everybody's legislation is up, this year they'll be putting in new bills. And so we'll probably see New York and some of the other locations do the same thing.
Well, if I take a look around at the different places that I go and have been going to, and if we take a look at refrigerants, not so much based on the temperature range, but the application. For basic pharmaceutical stability in academia, in any major university or research institution, if you walk up and down those halls, there's just room after room after room, and they're typically controlled, begin between +4 and +40. I see a lot of 18 to 20 degrees C. Is there any refrigerant along that temperature range and that application that you would recommend?
Yeah, so this is where you get into, you have to weigh the entirety of the project, right? So that's what's going to rule out the different refrigerants. So like if we take, for example, the -60 to -8 vaccine storage out of the picture, and you look at the other applications, the first place you would start there is the temperature range. Then you would cross off with which wouldn't work. Then you would simply move to what's the square footage, right? So when we talked about propane earlier, due to the limited charge, right, we can only cover a couple hundred square feet on a machine with the right amount of charge, and then we have to transfer to something else because we'll exceed the safe allowable limit by code. So it's really again, this is where you weigh everything in totality. Do we do separate systems? Do we do a distributed system? Every facility, every customer, every process is going to be different. When it comes to vaccine storage at -60 and below, however, there's really only one option there, which is we have to use current state. Again, because of charge restrictions, for an alternative is 508B for the low side, and then we'll be moving to 454C for the high side. And that's all that's available currently for that low of a refrigerant range. The rest of them, sorry, go ahead.
No, go right ahead.
Well, the rest of them, any of them are applicable above that. So you limit your 200 square feet for your propane, and then after that, any of the refrigerants, 454C, 454A, carbon dioxide, they all are applicable for these. Then it really comes down to the specific application. Is it local heat rejection in a room? Is it, remote rejection, water cooled? I mean, there's a few reasons we pick all that stuff. So it's a little bit of mad science.
So it's not as simple as saying, okay, it's that temperature range, we're going to use X. So I have to imagine
Correct.
This is where the design and engineering expertise comes in, as well as knowledge of local codes. And again, you mentioned heat rejection, air rejection, a lot of different things come into play.
Yep. And what's available to the facility as well, right? We can sometimes piggyback off of existing facilities infrastructure.
And it's time for our third and final poll. And it's how many of your clients are pushing for and will accept the cost of lowering a carbon footprint? I've been involved with a number of discussions and proposals, and customers absolutely want a CO2 system till they get the price. And then all of a sudden it kind of pushes back. So be very interested to find out if you're running into that as well. I've had a couple lunch presentations with some engineering firms, And I've just seen over the past year, the number of people who will raise their hand yes on that question has gone up. So we definitely know that, at least from my experience, that is coming up. So I'll be very interested to see what the poll results are. Give you another 15 or 20 seconds to answer that poll. All right, we'll close that. And Rebecca, what do we have?
So some customers, so about 80% have answered some, and then it would be none and all. So it looks like we're trending middle to the end here.
Okay, so about what I'm seeing when I'm out in the field. And this is the big question: is how are we going to balance that sustainability and the energy efficiency? I know, Nate, you hit on a lot of these points, but question that comes to mind is, all right, so let's say someone's building a cold room now, or they did it 2 years ago, or they're going to build one next year. There's a possibility that the refrigerant they're using now could become on the naughty list for Christmas from the FDA, the EPA, in terms of what they are allowing for refrigeration systems. Something like that happens. Is it possible to change refrigerants without doing a major overhaul to the design, or are there certain refrigerants that can be interchanged? Because I'd have to imagine you got to be really careful. These things are going to last 18 to 20 and 25 years as long as you're doing all the PM work. So there could be more phase outs along the way.
Yeah, people get kind of phase out fatigue, you might call it, which is just, every 10 years there's a new thing, which we understand as we're trying to become, again, more conscious, more green, make less impact on the environment. But it's a great graphic you put up here, because it is a weight decision, right? The new systems in their current format of traditional refrigerants, moving from HFCs to HFOs, you basically, right now manufacturers are working in terms of the compressors and componentry to get all that equipment rated. So we should probably see some improvement over the next year on those possibly being, how would you say, future-proofed. So if they were running 448 today, probably the next year we'll have the ability to possibly run 454 in that system. Again, that's if they're paired. A lot of times the new refrigerants, they don't behave exactly the same. So you lose capacity, more efficiency, et cetera. So it's really going to be tailored specific to an installation with very similar properties. So that's the most common one I would see would be 448 to 454. You can't convert to, say, CO2, right? That's not going to happen. Right. Completely different system.
So it's an ongoing project to try to determine how to do that, really.
It is. We're right, like I said, we're right at the edge of the approvals of now being able to utilize 454. And so now everybody's now that it's been approved through regulation, now we're catching up in terms of manufacturing.
Well, before we move into question and answer period here, I just want to kind of fill everyone in on Trane Technologies and FARRAR, and just how we cover the entire pharmaceutical value chain for our customers as well as you. If we take a look on the research side, we got a number of brands. We have FARRAR. We have ultra low temperature freezers. You can get a cold wall unit at 30 cubic feet or 311 cubic feet if you would like to have forced air technology. We have your typical lab grade solutions, under counter, benchtop, reach-ins, the 25 and 30 cubic feet. We've got freeze thaw chambers and control rate chambers, which go hand in hand when you're looking at storing something at about -60 to -80. We also have walk-in and drive-in cold spaces available. And a little over a year ago, we acquired Helmer, and they are the gold standard in terms of blood banking and of a lot of pharmacy applications. So when it comes to those types of accounts, blood banking, pharmacy, we've got a complete offering there. If I move along a little bit and I hit Thermo King, it's pretty much impossible to drive down any major throughway, expressway, or highway and not see a reefer truck or refrigerated truck that doesn't have the Thermo King logo on it. Well, it does a couple things. The first thing it did, it kind of helped everyone. If we go back to the height of the pandemic, when the vaccine was first available, now we had to distribute it. Luckily for the country, Thermo King has been supplying the country with yellowfin tuna from Florida, and they were shipping that at roughly -60 to -70 degrees C. So no one was going out for sushi, so there wasn't the need for the yellowfin tuna to be shipped. Thermo King was able to step in and do a tremendous job in terms of being able to transport that vaccine. Another way they really come in handy is if you're working on a project where you're remodeling a room, you're adding a room, typically business doesn't stop. So while that cold room is down and being remodeled or an entire area redone, you still got to operate. And Thermo King has on-site trailers, and we even have marine transport, so we can keep you up and running, even down to that -60, -70 degree mark. Just about a month or two ago, we bought a company called Clinge, and they can do the same thing. However, they have a redundant system, so we can store your -60, -70 goods, have a redundant system. Same thing on the formulation and fill storage thaw side. We have the FARRAR brands, and as well, we have the powerhouse of the Trane HVAC team behind us. And again, Thermo King can help out with the transport to market on the last mile. So that's just a little commercial about what we do and how we do it. I know it was brought up before day one and day two. We're not just interested in day one. We don't want to just install this equipment and walk away. We're very concerned about day two. And that's why we've got an unmatched fleet of trained technicians and third-party providers all over the country who are ready to step in and keep you up and running. Because when you're talking about a life science application, you've got to be up and running.
And going back to the efficiency standards and thing, this is a point that, the slide I kind of bring up, which is when we merge Trane and FARRAR together, if it's looked at in the entire building design, this is where we can make some gains. So, we can utilize, if you've already got a chilled water system running through the building, and you're doing electrification of heat or something like that, or if you're doing hot water, you can use, heat rejection from all your refrigeration systems running through a heat reclaim chiller in order to service the rest of the building. So it's a way to take a constant load and repurpose it. And we've worked with a lot of people lately, and that's kind of been our push. That allows us to go down to a refrigerant that's located outside the building that is an A2L, but as a GWP of 3 that's doing the primary part of it. And then we're using water cooling now inside to manage the machinery that we would normally install and rejecting that heat back there to be reclaimed. So when you think of it from a first step, where a lot of times we're having kind of secondary thoughts of the refrigeration to the rest of the building, the normal MEP kind of gets handled, and then refrigeration is kind of this secondary thought. If you bring it to the forefront, there's ways to leverage that and go back to your customer and maximize where they could get energy credits and just reduce their overall carbon again.
Moving on, we're very happy to take your questions and hopefully provide some answers. You can submit those using the chat window. I know Nate's going to be pulling through on those, so we'll take a minute or two and let you submit your questions. Nate, while they're filling out some questions, is there one area that in the entire cold room design that you think is fraught, where you can make the biggest mistake, where you have to really be careful? Is it the design? Is it the refrigerant you're using, or is it a combination?
Yeah, it's a combination. I mean, we see a lot of we follow up on a lot of installations where all the data wasn't properly gathered, so they're having problems maintaining, keeping temperature. They're having large issues with temperature fluctuations, so they're not getting the stability that they requested. There's always a challenge, right? It could happen from installation or installation. Lots of infiltration problems. Again, that's where you want to look at making sure you're using the right products, the right application, and make sure it's meet the standard again and goals, right? So you mentioned earlier, 18 to 20 year lifespan, proper installation, quality installation is going to matter. Following, having enough specs and the details, to make sure that stuff is going to live up to that standard. So Rob threw a question here. He says there's some new to market low temp biopharma freezers, which are using air as a refrigerant. Is there a practical expansion into using the same technology for room or warehouse scales? If so, what would be the most effective temperature ranges? So I've seen these systems. We've actually done some conversations with a couple of companies, and we're working through some things. And my biggest concern is the energy differential. So it's using a lot of power. Now, again, infancy of doing it. From that standpoint, there's going to be some small gains made. The big thing there would be balance again, how much energy versus what I'm getting, right? So we want to weigh, for a comparison, we'd want to weigh it with a CO2, that anything single digit, essentially, to say how much money is it going to cost me to run, right? And that's really where the weight's going to come in. Is it practical? Stephen Jewell just chimed in. He says, are there any electrical implications for using a less efficient refrigerant, higher amperage loads, something like that, like CO2? So just energy in general, they are slightly more intensive. CO2 is, inherently about 15% less efficient until you do some trickery. Really high ambience, it pretty much is always that way. So there will be some. Now, the funny part is when you look at some of these refrigerants where like 448 was a good example, where you lost a little bit of volume in its capacity, but you gained on efficiency. So its compression efficiency was much better. So you actually lost a little amp draw, right, that kind of offset the volumetric efficiency. So you're pushing more refrigerant around, you have to move it quicker, but you're not really using any more energy. So again, that's each one of them is going to have a different caveat. And then Rob just chimed in again. He says, are there facility leak detection requirements, as in ammonia, and facility emergency plans, which need to be considered when evaluating some of the new styles of refrigerant proposed in future use? Yes. So like currently on like A2Ls, you have to have isolation valves. Again, it's in its infancy on the approval. The UL is still doing some stuff, but a good example would be you'd have a liquid line shut off. So if you saw a leak, in the room, it would essentially shut the system down, isolate by closing that valve, and cut the system off. So no more would go based on a 25% concentration, right? So once the alarm goes off, it shuts down. So all that stuff is in the planning. There is a plan to do it all. So there will be some additional pieces, similar to ammonia, that will be leak detectors at the unit in the room. Any interstitial space, there's probably gonna have to be another one. And then isolation valves in your systems. And that's all we got for questions.
All right. Well, I appreciate everyone's time today. We picked up some information, and I certainly hope that you were able to do the same. So thank you very much.